Okay. Just wouldn't be a video without the first person being heard being Molly McNamara.
What?
Okay, here's a limit. Okay, so today we're going to learn how to formally, analytically, algebraically prove that these limits are in fact what we think they are. So first of all is the proper mindset with which to approach a limit. What sequence of thoughts should you go through every time you see a limit? Step 1. Is this function continuous at -3 or not? So many students skip that. And therefore, when I sneak an easy one by you that is continuous, and therefore you just plug the number in, people make it way harder than it's supposed to be. So don't let an easy one sneak by you.
How was it, Evan?
How was it?
Probably got a 5.
I can't feel my hand. I wrote way too much.
Yeah.
Is that a new job? Oh,
That's scary.
welcome back, Pocahontas.
Good one, Molly.
You remind me of Pocahontas. What?
Okay, now that that's out there.
I did your first one.
Step 1.
I just didn't.
Is this function continuous at -3? No, so we cannot use direct substitution to evaluate this limit. Step 2. Find the answer before doing any work. That's what I recommend. So we're going to get that fancy schmancy out. Go to y equals. Graph this thing.
You sound very unsure of yourself. Wait, this means that Instagram continuous means there's no goal.
Correct.
So
Or asymptote or jump means you can draw from left to right without picking up your pen.
my group seems
Okay.
a little slack.
So I'm going to do a zoom 6 and a standard viewing window. Ah, it's a line.
Hey, I said that.
I either expected a line with a hole or a line with a vertical asymptote. If the discontinuity at -3, I know there's a discontinuity at -3, right? If the discontinuity at -3 were a vertical asymptote, I would clearly see it. So I feel very confident that this discontinuity is in fact a hole, in which case I know this limit will exist. So let's figure out what the answer is first. Let's go trace, plug a number really close to -3 in. -2.99999. Hey, it's -5. That's great. Okay, technically you should approach it from both directions, but we have enough familiarity with rational functions to know this is in fact a hole, and holes always have two-sided limits that work. So, I won't actually know what you're doing, that you tested both sides. I feel confident this limit is going to be -5. So now let's prove it. So step 1, is it continuous or not? If it's not, step 2, I would recommend you find the answer before you start any work, just because the more you know. Step 3, NBC, the public service announcement. There's a new one with Kelly Kapowski. Who's Kelly Kapowski? Who's Kelly Kapowski? I'm not that old.
Is that a
Am
girl or a
I?
boy?
Girl! Zach?
I want to make sure.
Zach Morris and AC Slater.
Hi, bud! What's up?
How'd you do?
Yay. No.
Stevie Jew.
No, the actress is Tiffany.
I hit part B.
Excellent. Aw, you and John are twinning.
Walt Disney.
Walt Disney. It's
An
a Walt
Indian
Disney
thing.
sweatshirt.
We're going there this summer.
Where's Badoo?
So am I. Me and the other day, we just were not going to show up to class, but I showed up to class because Kelly kicked me out of the office.
Hey,
It's okay, it's okay.
let's get back to this limit, please.
Hey!
Thank you. So step 1, is it continuous? Step 2, figure out the answer. Step 3, find a new function that is equal to that one, except at one point, and that one point will be -3, because we're going to make a new function that's actually continuous through -3. So first of all, do you believe you can take this graph, which right now is discontinuous at -3, and by only changing one point, make it continuous through -3? Yes. So I want to find the function, I want to find the actual equation of that function. The one that is continuous through -3. And so in general, the technique you use whenever you have a rational function like this is factor and cancel. We call this the factorization technique. What's up? Oh, that's what you're going to recommend. You've done it. Okay, what does the top factor down to?
X minus 3, X minus 2.
Shh. I'm going to do this problem wrong. I want you to tell me why. So I got -5. Boom.
No.
What's wrong?
Because, first of all,
You can't.
that, when you cancel, that does not equal X minus 2.
Good. This function here is not equal to this function here, which is what I'm stating, isn't it?
Yeah.
It's not the functions that are equal. Those functions are different. They're only different at one point, but they're different. What is guaranteed to be the same, though, between them? Their limits. Right? When you only change one point in a function, you are not changing any of that function's limits. So, that just looks terrible to me. You have to write limit each time. It is the limit as x approaches -3 of x plus 3x minus 2. Something else?
I told you we were going to skip. I'm so glad you made it.
What?
Welcome I
back.
accidentally.
Helen.
Oh, I almost did. I got kicked out of the office.
Okay, so here's how it works. It is the limit of this that equals the limit of this. But the minute you get to a limit that is continuous, you then just use direct substitution. So I'm not writing limit anymore, right? Agreed?
What?
So the limit as x approaches -3 of this is equal to the limit as x approaches -3 of this function. I know that's true. Even though they're different functions, I know these limits will be the same. And this is a really easy limit to evaluate. You use direct substitution. So there you go. That is proof that this limit is in fact -5.
So when you plug the limit in, that's when you get rid of the limit.
When you do direct substitution, you no longer have to write the limit equation.
Can I just write -5? I feel like that's like.
Without showing any work,
No. Like.
from here to
No,
-5.
I get that. My question is.
I have another question. You have to write the limit.
The limit is x approaches -3, just like -5. Like -5 doesn't equal it. It's just a limit.
This limit equals -5.
Okay.
And here's what's confusing.
I want to make sure you could like.
Yes, and that's what's weird. We're talking about what a function does as the input approaches something.
And that would be -3.
And a lot of people instinctively want to say the limit approaches -5. But it doesn't. It's technically as x approaches -3 that never equals it. The limit equals -5. You're not approaching -5, you are equaling -5. So it's a little bit of a weird thing.
So as you
So negative 5 is
the
the thing
limit-
that it is
No.
approaching.
Wait. The limit is -5, right?
Right.
As you're approaching negative, as you're approaching -3.
Right.
So -5.
When you plug numbers insanely close to -3, basically, okay, here's the technical definition of the limit.
Wow, I guess we both.
How do you know when you are allowed to use direct substitution?
They said the function's continuous.
So without a denominator.
Yeah, there's no obvious continuity.
What I do.
Yeah, forget it. Let's do another one. There we go.
Is this what we learned yesterday?
No, basically the calculator part is what we learned yesterday.
Weren't you here yesterday?
All of this was the
Okay. The limit as x approaches 1 of x minus 1 over x cubed minus x squared plus x minus 1. Is this function continuous at 1? No, so I can't use direct substitution.
Are we supposed to know that by looking at it?
If we plug
Yeah.
1, you get a 0.
Plug 1 into the bottom.
Wait, why one?
Because
That's the.
That's what x is approaching.
And if it equals 0, then it's.
So because,
That's equal to 0.
even more importantly, just look at the function and identify where the discontinuities are. I know that. So, where does the bottom equal 0? 1. 1 cubed minus 1 squared plus 1 minus 1, that equals 0. So this function has a discontinuity at 1. That's the only discontinuity, actually.
That's why we're
Right.
approaching.
So, but the thing is, 1 also makes the top 0. If it makes the bottom 0 but not the top, what's happening to the graph?
Oh.
It's a vertical asymptote. And what are the limits at vertical asymptotes?
Infinity.
They don't exist. Just say don't exist.
Wait,
If it's a
so-
vertical asymptote, you just write does not exist.
So if it's only 0 at the bottom,
So if it's 1 over 0, it's
Right.
it's not.
Everyone's
If it-
If it's 1 over 0, the limit does not exist.
Correct. But this is 0 over 0, which we call indeterminate.
So we have to-
It could still be a vertical asymptote, but it could be a hole. Okay. So just how you want to approach these problems. Step 1, you identify you're not going to be able to do this limit direct substitution. That's because it's not continuous at 1.
And how do we do that?
Because it makes the bottom 0.
Okay.
Did the last one make the bottom 0?
No. The last one did make the bottom 0. X plus 3, and it was negative 3. But I found a new function, x minus 2 right here. I found a new function in x minus 2. Is x minus 2 continuous at negative 3?
No. I mean, yeah.
Yes, absolutely. So I direct substituted into this function. So the real question is, okay, how do I know evaluating this limit will give me the answer to this limit? And it's because the only difference between this function here and this function here is 1 point. Changing 1 point is not going to change limits.
I'm kind of confused on when we use the calculator to approximate the limit. Like, how can we accurately approximate this using a calculator? Like, it might have been, like, for the lesson, it might have been negative 5.1. Like, don't we know for sure?
That's why it's called an approximate.
Yeah.
We don't know for sure. It's an approximation.
Okay.
So we approximated that the answer to this was negative 5.
So then it's
That was a guess. Really, that's a guess. I didn't know for sure until I did this proof. Now I am convinced this limit is, in fact, the number negative 5, not something that's actually deceivingly close to negative 5.
And we verified this by doing a graph that is almost identical to the other one and finding the limit.
Right, and actually directly substituting into that.
Okay.
I have a question on when you stop or when you keep simplifying. Are we always going to keep simplifying to get to it? You understand what I'm saying?
You stop simplifying once you get to a function that is now continuous.
When you give us that problem, you always.
This one's discontinuous at negative 3. So is this one, but this one isn't. This one is continuous, so I stop there and direct substitute.
Got it.
Okay, let's do this next one. Okay, let's go back. Let's start back from the beginning. Step 1. Is this function continuous at 1? No, it makes the bottom 0, but it also makes the top. So this could have a limit. So, and this is an optional step, really, but I'm going to graph this thing and see if I can't get the answer before doing the work. So I believe we have x minus 1 divided by x cubed minus x squared plus x minus 1.
Woo!
So then I do a zoom 6, and I get this lovely graph.
I like that.
As expected, because this rational function... Now keep in mind, so far the two examples we've seen are limits of... What are these called? Rational functions. Rational functions we have studied in great detail in both Algebra 2 and Pre-Calc. So we know a lot about these graphs. For example, I know this has a horizontal asymptote at the x-axis because it's bottom heavy, right? So I was very, and I know it has a y-intercept at positive 1. Negative 1 divided by negative 1. So I'm very much not surprised by this graph. It's almost like a bell curve, but it's not. Bell curves involve E. So, you'll learn when you take E stats.
We can tell you.
You'll learn in IB Math.
I like how every time we have that moment, you have to be.
No, it's up to you.
What, a stats reference?
You always miss. But you punch me instead.
No, you can't call that a punch if it's really supposed to be a
But see, it's
fist
good.
bump,
It's
but
like
you
an aversion,
miss.
And she
it's like
doesn't
an
hit it, so I
aversion.
just go like that.
right? If you're just bad at fist bumps, you can't call it being punched. Okay. So here's our curve. I know there's a discontinuity at 1.
Yes.
It is clearly not a vertical asymptote, so it must be a what? Pole. So this limit's going to exist. Let's find out what it is. Trace point 999. 0.50005. I am guessing that this limit is 0.5, 1/2. Okay, let's prove it. What technique are we going to use to do this limit? What technique, more importantly, let me rephrase that question. What technique am I going to use to take this function and discover a new one that's identical to it except at one point? Divide, cancel factors. Your calculus textbook next year calls this the factorization technique. When you factor and cancel the common factor. Specifically, you are canceling the factor that is creating the 0 in the denominator. What is definitely going to be a factor of this polynomial? X minus 1. And it's going to cancel with this x minus 1. When it goes away, you're no longer going to have something creating zeros in the bottom, right? Okay, so let's do this. So we can factor this by grouping. What can I factor out of that group? X squared. And that's going to leave me with x minus 1. What can I factor out of this one? A plus 1, a positive 1, and it's going to leave me with an x minus 1. So I'm going to have an x minus 1 and an x squared plus 1. So factor by grouping. X minus 1's cancel, and I end up with the limit as x approaches 1. What is now in the numerator of my fraction? A 1. There's still a lot of us that because that canceled away entirely, they think the fraction is now gone. So make sure you understand that it is not. And the x squared plus 1 is still in the denominator. Now, is this function continuous at 1?
Yes.
Absolutely. So now we use direct substitution. And you do, in fact, get a limit of 1/2. Sweet.
So that's when you get the x squared plus 1, that's plug it in.
Right.
But how do you know it?
Does plugging 1 in make the bottom of this equal 0?
Oh,
No.
no.
So do it.
So do you have to plug it in each time?
I should take a look at it each time.
Okay.
Like, up, still a 0 in the bottom. Up, still a 0 in the bottom. Up, no more 0 in the bottom. Ding, 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 ding. Doesn't actually ding those.
Yeah.
I figured it out.
Okay. So those are the only 2 examples we are doing of factorization techniques. Okay? Notice, so far every limit we have looked at is a limit where the top of the fraction and the bottom of the fraction are both approaching what? 0. Okay? If you have 2 quantities that are both approaching 0, but you decide to divide them, so you got the numerator of a fraction approaching 0, the bottom of a fraction also approaching 0, what is their quotient going to approach? You never know. It could be anything depending on the speed at which they are approaching 0.
Are we adding out of errors?
Okay? No. So I'm just recapping what we've looked at. We call these indeterminates. Whenever you have something like 0 divided by 0, that's an indeterminate. The rate at which the top approaches, well, 0 divided by 0 is undefined. But the limit is not undefined. The limit could exist. Because it all depends on how fast the top's going to 0, how fast the bottom's going to 0, and are they both going to 0 at proportionally relative rates, hence canceling each other and creating 13. Right? Does that make sense? At the same token, that's not the only type of indeterminate there is. Here's another type of indeterminate. Infinity over infinity. If you have two quantities, one of which is exploding to infinity, another of which is exploding to infinity, and you're dividing them, if they're both going to infinity at relatively the same rate, their quotient could be -9. Okay? Now, if the top is going to infinity way faster than the bottom, then that fraction is going to infinity. If the bottom is going to infinity way faster than the top, that fraction is going to 0. So that's another type of indeterminate. They don't just have to be 0 over zeros. They could be infinity over infinities, which we will also be looking at eventually. Here's another type of indeterminate. Infinity minus infinity. Right? What's infinity minus infinity? A lot of people want to say what? 0, but what if you got to think of this not as you have something that is infinity. You can't. Infinity is not a number. You instead have a function that is approaching infinity minus another number that is approaching infinity. If that first one is approaching infinity just barely proportionally faster than the second, it's going to be some positive number. If the second is going a little bit proportionally faster than the first, it'll be a negative. If this one's going to infinity insanely faster than this one, then their difference is infinity. Right? So it could be anything. For things that are going to infinity. What about 0 minus 0? What do you think? If you've got a quantity that's approaching 0 minus another quantity that's approaching 0, what could their difference approach?
Anything.
No, actually 0. That's not an indeterminate. Here's another one. 1 raised to the infinity power. Now, I'm not talking about raising the number 1 to the infinity power. What would the number 1 raised to anything that approaches infinity be? It would be 1. I'm talking about a quantity that is approaching 1. Never equals it, but is getting insanely close to it. Raised to a power that is getting insanely close to infinity.
When do we know when you're just messing with
Okay? I'm not messing with you. This is real. So there are lots of types of indeterminates. Tell you what, let's Google it. Google.
It's a number, okay? Just shoot
I go with 6.
I think Google has a nice
I bet they just
indeterminate. Not certain is basically what it means. Indeterminate means, wow, 0 over 0. What does that tell me? Nothing. I have to investigate further.
Forward into your call.
How's PB? I like the
Okay, here you go. I don't know if you can see because it's small, listen, but here's a bunch of indeterminate forms. Now this does not literally mean if you take 0 and raise it to the 0 power, you get undefined. But if you have a function that's approaching 0, raised to a function that's approaching 0, that power could actually equal something. 1 to the infinity. Infinity minus infinity. 0 times infinity. If you've got a function approaching 0 times a function approaching infinity, which one dominates? Right. Whichever one, or maybe the root is moving at the same rate and you get 3. Okay? Infinity raised to the 0th power. I mean, so lots of indeterminates. Okay, let's do another one. Ooh. Now, this is not a rational function, so the factorization technique will not work. We're not going to be able to factor and cancel common factors. Again, don't let me trick you by putting a much easier limit on the quiz than you realize. Is this function continuous at 0?
Yeah. No, it's 0. It's 0.
This is a.
It is not. Good. But, what if on Friday's quiz, I made this same function, but I had the limit approach
1.
3 instead?
3.
Then,
Continuous.
just plug 3 in because it's continuous. Right? You're going to get an answer of 1/3. Boom. Piece of cake.
Wait.
Okay? So don't let me trick you. Don't automatically assume you have to use these techniques.
Okay, so if it's 0 at the bottom, you keep going. But if it's not, then you just plug it
Not if it's
in.
more than, not if it's more than zero.
So she's talking about if there's a 0 in the bottom.
Wait, that right there is the limit that's not exists, right?
Why not?
For what?
No, this is 0 over 0.
It is?
Yep. Yeah, this is a 0 over 0. Yep. Okay.
So is this like infinitely many?
So again, listen, guys, way too much noise.
I thought 0 over 0 is indeterminate.
0 over 0 is indeterminate.
But is it the limit?
No.
But are we just? Oh, you said that was 3 when you plugged in.
Right.
Didn't you say the limit though? It could. Are we finding a limit? So it's gonna be anything? It's 0 over 0.
You're right, it could be anything. I need to find out what it specifically is for this problem.
So it's
There is a bit answer
Oh, there is.
for this one. Could I create another function whose limit at 0 is a 0 over 0, but the answer is 13? Yeah. But it's not. But this particular equation has only one
This
correct
one's
answer.
0 over 0,
Right.
which is undetermined.
Which is indeterminate, yes. Okay. Okay. Let's start from the beginning. Here we go.
Woo!
We're gonna get through this one nice, smooth, uninterrupted explanation. Oh, good start.
No, but you just had to spell something. Keep going.
How to spell what?
Indeterminate. Is it mint or a nit?
Net. N-A-T-E.
N-A-T.
Indeterminate.
I spelled it wrong. Wow, why would you do that?
It's discriminant that has the NT in the end.
Okay.
Indeterminate. What is it for matrices? Determinant?
Yeah.
Is there NT?
Yeah.
Yeah, that's weird. Alright. You ready? Here we go. First thing I do is, can I use direct substitution? No, I cannot. Step 2, let's get the answer first. So y equals, I go parenthesis, square root, x plus 1 minus 1, close parenthesis, divided by x, do a little zoom 6. Bada bang, I do not see an asymptote at 0. Right, I don't really see much of anything anywhere.
There's a weird thing right there.
That's a weird thing. Let's trace really close to 0, 0.00001. And I'll put 0.4999875. That was to the right of 0. I'm gonna try one to the left of 0. Negative 0.0001. 5.000125. So what do you think?
1/2.
Looks like another one with an answer of 1/2. So I'm going to guess that the answer is 1/2. Let's prove it. Now,
Wait, but why on the right side it wasn't?
they were both close to 5. 4.99 and 5.00. Or sorry, 0.499 and 5.00.
So limit's 1/2.
1/2. Okay. This is called the rationalization technique. Okay? I want to take whatever part of this fraction has the radical and rationalize it. How do we rationalize radicals?
Square root it.
Multiply it by its conjugate. Squaring radicals does do that, but is there a rule that says I can square a fraction without changing its value? No. There is something that says I can multiply the top of a fraction by something as long as I multiply the bottom by the same thing, right? So if I multiply the top by radical x plus 1 plus 1, that is called the what? Conjugate. Guaranteed that radical goes away. So we multiply the bottom also by radical x plus 1 plus 1, the conjugate of the top. So the top we have to FOIL. So, 4 letters, F-O-I-L. So we multiply first. What do you get when you multiply those radicals? Yeah, the radicals cancel away. You get x plus 1. You get a plus radical x plus 1. A minus radical x plus 1, which by no surprise, those cancel. And you get a minus 1. Now the bottom I'm not going to distribute. I want to leave that factored out. Because what is it in the denominator that is causing the discontinuity? The x. So that is what I want to cancel away.
Wait, don't those X's and both the top one cancel?
Those cancel, these ones cancel, so what are you ultimately left with in the top?
X.
X. So this is the limit as x approaches 0 of x over x radical x plus 1 plus 1. And what happens to those x's?
They cancel.
So here's where I now get my new function. The limit as x approaches 0 of 1 over radical x plus 1 plus 1. Now, is this new function continuous at 0?
No.
Yes. Too lazy to do it.
Does plugging 0 into the bottom make the bottom equal 0? No.
Oh, so that means it's.
It is.
This is continuous.
Okay.
I can now use direct substitution.
Is it like a number? Plug it in. Is it
Okay, yeah.
So we get 1/2. Yo.
Continue.
Yeah, you don't get into
Yeah, bro, how did you cancel the minus whatever?
Well, dog. Wait, what minus 1? This one?
Yeah.
This one.
Oh, wait a second.
What's combined like terms?
There,
Plus
no,
1
I
minus.
was trying to cancel it out from the bottom.
Oh, no. That's not called canceling.
Also, this is the,
That's
when
called
you're
chunking.
doing the conjugate, that's what you're doing in the first problem we did with the factoring.
Well, that's a different technique. That's called the factorization technique. But it is all about canceling.
About that,
So they're both trying to.
This one we use conjugates to rationalize to cause the
It's
cancel.
called conjugation.
Sure. Listen.
Conjugation, sir?
Listen, you bunch of squirrels.
Oh man, that hurts my feelings.
That's
We're
funny.
different. I like.
You guys are just so squirrely. What? My chipmunk face. You can't do better,
Do it
dude.
again!
Let's see.
What? Do it
Wow,
again.
good chipmunk face.
Do it again. I never said that. I want to see it. I missed it. Yeah.
You can't keep your cheeks puffy while pushing your teeth out. That's embarrassing. I have a new theory. You can't have your teeth sticking out while inflating your cheeks without making a fart noise.
Because you have space in between.
Right, yeah.
Science.
Or drooling all over yourself. Ha!
I did it.
That's a skill to be proud of. All right.
That's right, everyone.
Whoa! I think that's the first time I've ever said fart on a video. That's great. All right.
Wait, are we recording?
It's over.
Example 4. Now,
He never puts it on.
Yeah.
these. Well, I do want to do it because some of the people miss, like especially like beer and drinks. But I don't know. We got all day tomorrow. We'll see. Yes. I said, yeah, I'm fine with that. Okay. The limit as now this one right here.
That was so lame.
These next two limits we're going to look at are world famous historic limits. But for now, we are not going to have the algebraic method to prove their answers. So mostly, I just want to look at them. This is an intriguing one because a lot of students look at it like this: as x approaches 0. What does 1 plus x approach?
1.
1. So as x approaches 0, the part inside the parentheses approaches 1. And as x approaches 0, what does 1 over x approach?
1 over 6. I mean, at the 5.
As x approaches 0, 1 over x approaches infinity or negative infinity.
What? Because it's an asymptote.
Right? If you do 1 divided by an insanely small number, you get a big number. Okay, so here's what we have. I've got the part inside the parentheses approaching 1. I've got the exponent approaching infinity. And what do a lot of students think the answer is? 1. Because they think, oh, that's just multiplying 1 times itself a crazy number of times. It's not. Let's do this on our calculator and see what the answer actually is. I hope this blows your mind.
It was like 4 or something.
Wow, it's just.
Parenthesis 1 plus x
You ruined it,
Alex!
You ruined the prize.
Sorry.
raised to the 1 over x power. We hit graph.
I already know what happened. Want to know why? Alex.
It's a very simple looking graph. It almost looks like an exponential. So if I hit trace,
You're killing killing me.
and I plug a number really close to 0 in,
It's okay, Alan. I'm always bad.
I get 2.71828. Or let's plug a number even closer. Wait, what you say?
2.7 inches.
What? What?
Oh my god!
E?
I thought that was a very bad idea. It sounds like Whoa!
It's E!
Is my calculator just messaging?
Yeah, what are those dots over there?
Yeah, we were really excited that was what was going on.
I have them on mine too.
Yeah, because what's happening is, in general, negative should
Awesome.
work because when you have a negative raised to power is imaginary. But there are certain negatives that, like, it's an odd radical that work. So those are, you can like trace those points. Those are like,
You got a comment.
I can't remember.
Yes, I'm all.
I did
that.
It looks like
I
But the thing is, you should do
I know how I got a
points that, you know, you actually can take roots of negatives and get real answers. It's an odd root. So those are just roots of negatives that work. Hey! Is that pretty cool?
Yeah, that makes sense because X can be.
Creepy like that. E is the creep of mathematics. Just always hanging around, just watching you.
Equals E.
But isn't that interesting? Listen. Now, what is the limit as x approaches 0 of 1 raised to the 1 over x? That is also a 1 to the infinity. But that literally is 1 times itself a bunch of times. That is for sure 1. So there's a difference between actually raising the number 1 to a very, very big power, or raising a number really darn close to 1 to a really large power. Right?
But don't you do parentheses first anyways? So it wouldn't be boiling. You don't do the parentheses first.
Here's the thing. As x approaches 0, what does 1 plus x approach? 1. But does it ever equal 1?
No.
No. It's going to be a number insanely close to 1. But even a number insanely close to 1, when raised to a power, can become a big size.
Okay.
If the exponent is big enough. What is the exponent here? Infinity. So, yeah, it stands to believe, yes, a number insanely close to 1 raised to an insanely huge power, apparently in this case, creates E.
I think you do it great. So you just
Of course I did. It's world famous.
in on the point.
Alex is having fun right
Zoomed in
now.
on the point.
Now, do you know how in calculus you will learn how to do this limit by hand? And guess what you use to do this limit by hand in calculus?
Math?
You actually use logs.
Oh,
Who
I was
said
gonna
that?
say compass.
Nice guess.
I
said math.
You use a natural log. And what is a natural log a base of? E. So that's how that works out. Yeah.
Oh, because it's E. No duh. I knew
When I
duh.
zoomed in on one of the points, I got a cluster of points very similar to a line.
You will.
Okay.
And if you keep zooming, you'll see the cluster get bigger. It's actually, those points are actually densely packed, but yet there's always space between them.
Okay.
It's a weird concept. Yeah. That blows your mind. I got a piecewise for you that'll make your head explode. Here's another world famous limit. The limit as x approaches 0 of sine x over x. In calculus next year, you will prove that this limit equals 1 using something called the squeeze theorem.
Ew.
I can't say it without saying it.
Don't say it like that.
I'm like the common man.
What?
Nobody?
I think
Yes.
you're crazy.
97.1 The Fan, Common Man Company. You know the baseball pitcher Zach Greinke? He cannot say his name without saying it like that. I can't say the squeeze theorem without saying it like that. The squeeze.
I really hate you right now.
Ow! Okay. Plug that one in your calculator, plug a number close to 0 in, you'll get 1. I'll leave that one up to you. Oh, one-sided limits. We'll save this for tomorrow, but we got really far today. Good work. Here's your homework. Nice job, team.
Oh, okay.